Welcome back, everybody, to the next session here. It's my pleasure to introduce Robert Niven here. He's no stranger. He's been around the MaxEnt community a little while now, and he's basically going to continue on what we were talking about in the previous session on the maximum entropy or production principle. So, take it away.
Thank you, Adam. And first of all, I'd like to extend my thanks particularly to Philip and to the rest of the organisers for the invitation to come here and this opportunity. So I'm going to talk today about this MaxEP principle that we've been hearing about this morning, and some maximum entropy analyses which relate to flow systems. So what I'm going to talk about, give a quick introduction, then I'm going to talk about James MaxEnt. So I'm actually going to go right back into delve into the mathematics and the meaning and the structure associated with MaxEnt, and I'll apply that to a thermodynamic equilibrium system, just so that we're on the same page, if you like, so we all understand what we're talking about and what are the meaning of some of the different terms. And particularly I'm going to go to this what I call a potential function, or you could call it a negative Massieu function, and the meaning of that term in thermodynamics and elsewhere. I'll then briefly touch on the MaxEP principle itself, and then embark on an analysis of steady-state flow systems using MaxEnt, and see where that leads us, and draw some conclusions from that. And finally, I also talk in reference to an example system. One of my favourites, of course, is fluid flow, so we'll talk about that. I'll just briefly mention, some of you are aware of this, some of you are not, that Roderick Dewar and myself and two others are organising a MaxEP meeting in Canberra in September. September, of course, is spring, and you have the balloons. I think it's the only capital city in the world that has balloons that hover over the city. So quite often you'll wake up in the morning and find them over your house and so forth. But the purpose of this meeting will be to talk about the theory and also a number of different applications, and quite a lot of different applications. Not all of them, I must say, are correct, but quite a lot of applications are coming along in using this hypothesis or principle. So first of all, what I want to talk about is systems analysis. And I'm going to consider a probabilistic system, and I think this is a good way of trying to understand how it is we apply MaxEnt and why we apply MaxEnt. So we have a system, and it's really important it's made up of some discrete entities. You don't actually have a continuum, and so those discrete entities traditionally have been atoms and molecules, but they don't have to be. They can be anything else. And so I've got a lot of different examples there. Even human systems can fall into this framework. And what's important here is that you've got some system and you've got something outside the system. You always have an inside and an outside. You never analyse, well, you can think of the entire universe, but you've always got some system in mind when you're applying this framework. And so James came along in 1957 and said that we maximise an entropy subject to constraints to determine the least informative position of a system, or description of a system. There's actually an older idea, which of course was given by Boltzmann and Planck, which I'm going to call the max prob principle, but it's very similar. In fact, the mathematics is the same, but the rationale is different, is that we're maximising an entropy subject to constraints in order to seek the most probable state of a system. And I'll have to try and explain what I mean by that. But traditionally, if you look at all of the engineering textbooks, when they talk about systems analysis, they'll give you a whole bunch of different principles, basically the conservation laws. So these are the fundamental principles that we've got. We don't have many. So we really only have four sort of conservation principles. Maybe there's some more esoteric ones that I haven't listed here, but essentially there are only four. And then there's a bunch of relations here which are sort of grouped together, transport relations and constitutive laws and so forth. And these are how we do our traditional systems analysis, and this includes fluid mechanics. What I advocate is we're going to scrub out these, and we're going to say Jane's MaxEnt gives us another principle, and not only is it one more principle, this is the primary principle, and these are constraints, subject, that this principle is subject to. So I would actually invert the whole analysis because it's a probabilistic system. It's not a deterministic system. And so I'm going to contend, and we've seen some examples today, that MaxEnt enables dramatic simplifications to systems analysis. We've seen that in thermodynamics. That's what we've seen for 100 years and more. But what I'm going to do is map that into a generic context, which is exactly what Jane's tried to do. You can analyse old phenomena in new ways and also new phenomena. And there's also this tantalising possibility of model closure. And this is, as a fluid mechanicist, this is my primary interest. But we've got to keep in mind very much exactly what James would have told us, is that this is inference. This is a probabilistic analysis. There's no certainty. Your predictions may be wrong. So you've got to accept that possibility is there. The other aspect of this is that you lose a lot of information. So you throw away the dynamics, and then you can argue that the dynamics don't matter and you can predict various things, but maybe in some circumstances, depending on the questions that you're asking, maybe the dynamics do matter. So this is not going to tell you everything. It's like thermodynamics doesn't tell you about kinetics. They're two different theories. So let's not try and expect too much to come out of this type of inference. We're only going to be able to infer certain types of things. Okay. I'm using Ariel's wonderful little device here. You can see this line. This is my interpretation. I think it's the most fundamental reason why we apply MaxEnt, and I have yet to be convinced by any arguments to the contrary. So what I'm going to do is I write a generalized form of the Boltzmann principle, and you'll notice here Boltzmann actually didn't write this equation, Planck did. They used a weight. This is actually a probability. So what we're trying to do is we're trying to maximize the probability of a system. So we're trying to seek its most probable state. And then if we have some probability that describes the system, we can insert that into the formula, and subject to various limits, we can come up with this equation, which you recognize as the relative entropy. If we want to map that into a continuous framework, then continuous function here, we can do that as well. This is analogous. If you must put information theoretic interpretations to this, I would suggest you use the method of types by Chizar, because this is more or less identical to this, just different names. And the insight here is that in some situations, this may not be a multinomial probability in here, and then you end up with different entropy functions. So I'll open that door, and I know that a lot of you are going to sort of try and hit me with a 2x4, but I'll just suggest to you that accept this for the moment. This does not affect the rest of what I'm going to talk about today. But I'll just also mention quickly that here you've got a definition of entropy based entirely on probability and nothing else. So just think about that. All right, so what I'm going to talk about now are different types of systems. So thermodynamic systems are the obvious example, the first example historically that people thought about. And there are two different flavors of these, but essentially they're constrained by their content. So you have a box, and you're saying this is the content inside the box. So I've got energy, I've got volume, I've got numbers of particles of different types, and so on. And then we can write down, because it's a probabilistic system, we can write down what is the joint probability of particular instantaneous values of those contents. So that's our probability over which we're going to define our entropy. And so, for example, probabilities of occupancy of energy levels, volume levels, and so on. If we consider an isolated system, our entities are molecules, and so this is what people call the microcanonical ensemble. But alternatively, we can actually consider entire systems as our particles and do our combinatorics on those. in which case we're dealing with one of the various canonical ensembles. And it doesn't matter. I mean, the mathematics don't change regardless of what it is that we're trying to analyse here. And the essential point is we apply a MaxEnt and we predict the equilibrium position of the system. Now, on the other hand, let's consider a steady state flow system. We've got now an entire control volume. Now, how do we describe the system? Well, it's constrained. In this case, if we've got a whole control volume, we consider there are constraints on fluxes around this boundary, so mean values of fluxes around the boundary, and then our probabilities are defined on instantaneous values of those fluxes. So that's a whole control volume. Alternatively, we can consider just an infinitesimal element within a fluid flow, and again we can consider mean values of fluxes through that element, and then we've got a probability of particular instantaneous values of those fluxes. In either case, you can see the representations are quite similar. We are going to apply MaxEnt, and then we predict the steady state of the flow system. We can take this even further, and there's a very nice talk earlier about biological networks, which I see is strongly connected to this. You can imagine a generalized network, so this could be a traffic flow network or a communications network where you've got flows between nodes, and in principle you can have any connections between any nodes, and so we're going to constrain that here by flows between nodes. And then we've got probabilities that are defined on instantaneous values of flows between nodes, and so on. You see, you can see how this will extend. Roderick Dewar, apart from contributions in this area, has also contributed, I think probably even more fundamentally in biology, considered a biological system where you've got flows through some reactive space, and you've got some agents here, some biological agents. And so these flows may be energy and various resources passing through a system, and then you end up with joint probabilities associated with agents which are consuming those resources. And so this gives you a probabilistic biological population model, which is very interesting. And in either case, you can see with these types of setups, we're predicting a steady state of a flow system, or there are flow systems of different types. Okay, so how does James' MaxEnt actually work? I'm sure all of you have seen this, or if you haven't, then you need to go and make sure that you have seen it. We're going to maximize an entropy. Of course, we're using a relative entropy, subject to some constraints. When we do that, we end up with a Boltzmann distribution. That's fine. We've got some multipliers in there, which we determine in conjunction with the constraints. We've got a partition function and a log of a partition function, which is known as the Maxell function. And just to recall how this applies in the simplest thermodynamic system that you can possibly imagine, we have molecules being distributed amongst energy levels, which is a sort of traditional diagram that we see. And we have a mean value of energy of the whole system. And so we apply MaxEnt and we get these equations. And this doesn't immediately mean anything to us until we think about it and think, well, what is this entropy here? Well, this entropy is actually related to the thermodynamic entropy, S. And what does this multiply here? Well, this actually, you can show with various arguments. You can't prove, but you can understand it with various monotonicity arguments and so on, that this must be related to reciprocal temperature. And so you can put these in, and then you end up with the sort of equations that you see in thermodynamic textbooks. And so there you have it. So there's a thermodynamic description. Making a slightly more complicated thermodynamic system, I'm going to throw in two constraints now, mean energy and mean volume. I didn't correct that picture, but there should be, it's like a matrix of levels now. Now you go through your MaxEnt and you come up with this, and you can make some identifications and come up with your thermodynamic equations. And this time they're in terms of, collectively this is known as the enthalpy, or enthalpy on temperature. Okay, so I hope you're with me so far. Then the great beauty of MaxEnt is that you have this mathematical structure. So I should alternate so some of you can see half the time. So you have this beautiful mathematical structure where you have the maximum entropy. I'm going to move some terms around here to come up with this negative mass U function here. And then you have first and second derivatives, and you end up, because of symmetry, you end up with Maxwell relations, and also because of the relation between these Hessian matrices, effectively you end up with a Legendre transformation. And this is generic. This is not thermodynamics. This is generic space of what I like to call the Jaynes relations. So any system that you analyse with Jaynes method. So we go back to our first thermodynamic system, and here's our maximum entropy, our potential. Now look at this. What is this? This looks familiar. This is the Helmholtz free energy. All I've done is I've multiplied this potential by kT, and I've come up with the free energy. And this is what I'm going to argue is the meaning of this potential. You've got your derivatives there, first and second. The second derivatives come through as functions of your susceptibility. So here's the heat capacity there. And we've got a Legendre transformation between, this is known as the Planck potential, free energy on temperature. That as a function of 1 on T can be mapped over between that and the entropy as a function of internal energy. Okay, let's try that. Second thermodynamic system we considered with the two constraints, U and V. Well, here it comes through. There's our entropy, there's our potential, here's our Gibbs free energy. Here are the derivative relations, and you now have a matrix of susceptibilities, and you see that there are three susceptibilities that we're familiar with, and Legendre transformation. Okay, so this is thermodynamics. That's how it works, because the Jaynesian structure maps over into this particular example. Now I'm going to make a couple of interpretations along the lines of what Jaynes told us. The first one was that he developed this concept. If you consider the variation of a constraint, you can think of one of those two terms here as a generalized work and another one as a generalized heat. And when you go through the mathematics, you end up with a generalized Clausius equality and a generalized potential. Here's our phi again. And you can see that if there's no change in these Lagrange multipliers, then this is a generalized weighted work. And so changes in this, or rather we can think of this, if we think of a system, it can give up work to its outside. Remember, there's always an outside of a system. It can give up work to the outside, and in the old days, in thermodynamics, they were thinking in terms of availability concepts and so forth. And so a system is going to minimize this, or you can argue a system will minimize this function phi because it's minimizing its available work relative to its environment. So this carries over into this framework. Another interpretation, which I think is actually stronger, is we can consider this generic entropy of an entire universe, and my entire universe consists of the system and its surroundings. And so changes here are the sum of changes within the system and outside the system. Together they must be greater than 0. But now this one we've already worked out. How can we change the entropy outside the system? Well, there's a whole bunch of things going on outside the system that have nothing to do with the system. You know, something in the Andromeda galaxy is not affecting a system here on Earth, right? So those things don't have any influence. The only way that there's a connection between the system and its surroundings is by transfer of one of these generalized heats. And by doing so, what we end up doing is we can consider this change, if it has any influence on the system at all, does so through changes either in the constraints or the multipliers. And so I'm going to call this a generalized entropy production associated with the system. And so you can see you have this potential phi is a negative sum of changes of entropy within and outside the system. And together, because this is in a negative sense, this function must be minimized. It must be, the increments here must be less than 0. And so we should be seeking a position of minimum phi, however we're analysing a system, in order to seek its most probable state. And that's what we see in thermodynamics. So when we apply this to our thermodynamic system, the second example, just to make something slightly more complicated, is, so here's our G on T, our Planck potential. We have change in entropy within the system, change of entropy outside the system. So this is the increment associated with transfer of heat and pushing entropy outside the system. We call this the enthalpy on temperature, but I'm also identifying that increment there with a negative change. This is an increment of entropy which is produced and dumped outside the system. And so now you can see there's a competition between two variables here. Both of these could move in the same direction. We could maximize this and maximize this, and then we'll be able to minimize this. Alternatively, one can be maximized and one can be minimized, and as long as the net change is such that our G on T is diminished, then that process can go. So it can actually act. And so you can see, and the chemists talk about this, that they're very familiar with what they call entropic processes and enthalpic processes. I think we have a better understanding here that all of these are driven by maximum entropy. It's just entropy of different compartments within the whole universe. Okay, I won't go through this in detail, but you can apply James' framework to any other thermodynamic system you like, and you can even invent new ones. And he did this in his paper. Now actually, incidentally, all of these functions were derived by Gibbs, just they've been long forgotten. So this one doesn't even have a name. This one is considered the stress-strain ensemble. But effectively, we can do lots of things in thermodynamics that people haven't done because we have this Jamesian framework to do that in. Okay, so to summarize that, James' framework gives us our existing thermodynamics, as told to us by Massieu and followed by various people, including Planck and Guggenheim and a few others, have implemented these Planck potentials or Massieu functions. Gibbs unfortunately was thinking in terms, or fortunately or unfortunately, he was thinking in terms of energies. And so he devised a free energy concept. It's a little bit deceptive because it's not actually anything to do much with energy. But anyway, nonetheless, thermodynamics is cast in this framework. Okay, the Maxell Principal. Again, I'll thank Tim for making a nice summary, so I don't have to say too much here. Let me just move that out of the road there. So the idea is that we have our, for example, the climate system with heat flux in from the sun and then radiated out into deep space. It's setting up a temperature gradient between the equator and the poles, and the argument of the MaxEP idea is that the system is seeking a state of maximum entropy production. And I attended one of these meetings in 2007. I came across this idea, and of course it's deeply puzzling as to why this should be the case. So I was determined to look at the theory. One of the things that also struck me was these diagrams here. Tim presented this one. So you have a connection between two entirely different systems. Here you have a Baynard cell, and as you increase the distance from equilibrium, you can think of this is a Rayleigh number, you force a transition. This is the entropy production here. There's a transition somewhere between just a purely conduction mechanism and something which in this case involves convection, so some nonlinear process going on which dramatically increases entropy production. If you plot a similar diagram, this is given by Philip Maceman, of a chemical system where you have a chemical gradient that can be exploited, and you plot, here is sort of, for example, a plot against chemical affinity. As the affinity increases, you have processes in this range which are just linear chemical processes, but there's some transition, and then we have the onset of life. So you have biological processes here. So there's a connection between fluid mechanics here and life. And so this struck me that this is really profound, and this is something that's really worth spending some time on. And a number of people before that time and since that time have applied this MaxEP idea in many different types of systems. and also in many different flavors. So where does this come from? What does it mean? Can we try and have a theoretical understanding of the theoretical basis of this principle? Okay, so now I'm going to talk about steady state flows. And what I'm going to do is I'm going to consider, because I'm an engineer, I consider a control volume. So this is the description where you've got flow of fluid in and out of a control volume, and that is going to be constrained by mean values of particular fluxes. So I'm going to consider, in this case, an infinitesimal area element that has instantaneous values of particular fluxes, and there are mean values of those fluxes which we can use, which we have some knowledge of or access to. I'm forced to use the local equilibrium assumption. I don't like it. I'd like to get rid of it. But nonetheless, let's keep it there for the moment and see what happens. So if you look at the textbooks, for example, de Groot, or any book that actually talks about entropy production, not many people do. This is the equation that's given for the entropy production. So this is entropy production per unit volume within an infinitesimal element of a fluid system, a fluid flow system. And so here you've got a heat component, a chemical component. There may even be some fields in here, and there'll also be a momentum component. And that's fine. The trouble with this equation is we don't know all of these quantities. Remember, we said that even if we know these values of these mean values of fluxes, we don't know the corresponding gradients. And so usually we can't even work this out. And if you read the books that actually tell you how to work this out, you'll see that there's just a tremendous list of assumptions and so forth that go into any calculation. So people don't generally calculate entropy productions using this principle. Okay, so we have something that we can't calculate. But can we apply MaxEnt? And so this was my interest here. So what I considered, here's my infinitesimal element. I've got instantaneous values of fluxes through an element. I've got mean values are the constraints. I can consider a joint probability of those instantaneous fluxes. So I can write down an entropy function, and it's a different entropy function. It's not the thermodynamic entropy. This is the flux entropy. And when you do that and maximize that subject to the constraints, of course, you get a Boltzmann and you get a maximum entropy, and then you scratch your head and think, well, these zetas, these are my Lagrangian multipliers, what do they mean? Well, go back to our entropy production. We have a term that looks like this, and so I think it's actually quite natural to map each of these Lagrangian multipliers to the corresponding gradient. And when you think about this even more deeply, because you can turn on and off any of these flows, they're linearly independent, so you must be able to do it this way. So this is the only sensible solution. There's just a proportionality constant that flies in there. And so you end up with an equation that looks like this with a constant in there, and I'm going to write it in this form, and then I'm going to invert this or flip these around, and so I'm going to have, here's my negative mass U function, is the sum of an entropy within the system and an entropy outside the system. So it's exactly the same as what we see in thermodynamics. And if I wrote this in a differential form, then I'd say that d of this is d of this and d of this. So it's a sum of changes of entropy within and outside. There's a connection between changes of flux entropy dumped outside the system and the thermodynamic entropy. So that's a very interesting connection. And so that's why we end up with this term here in terms of something that is connected to the thermodynamic entropy. Okay, so again we have this situation where we have a function that we're trying to minimize, which can be is a sum of two components, and depending on the various combinations of these components, we can have three possible situations which minimize this function. Two of these, you can see, give a Maxell principal, but only two, not three. It's not a universal principle. And I don't think that you can take this any further. I don't think you can do anything more to this to insist that there is a universal Maxell principle. I think that is fundamentally unsound. So let me let me be quoted on this and we'll see if I'm right. So we can derive a local MaxEP principle, but it's not universal. And it's actually analogous to a minimum enthalpy principle in thermodynamics. And when you actually think about the history in thermodynamics, before Clausius and so forth really got to grips with this concept of entropy, that's what they did. They minimized what we would now call the enthalpy of a thermodynamic system. That's how they analyze systems. So here's the analogy here. There's the entropy within the system, two different entropies. Here's an entropy, a change in entropy pushed outside the system. Here it's dumped into a bath, or the rest of the universe. Here it's dumped into the reservoirs, but it's still inside and outside. And I also note that at least in Australia, Australian chemistry students are taught the minimum enthalpy principle as part of their high school, year 12 chemistry. So we still do it. It's still important. It's just, this is not, minimization of this is not a universal principle. It's useful in some circumstances.
Robert?
Yes?
You could go back and question about the irreversible thermodynamics equation.
This one?
Go back.
This
one more?
This one?
This one, okay. Remind me, where does this come from?
Where does it come from? Well, it comes from de Groot's textbook. But where does it come from fundamentally?
Exactly.
Yeah.
Let me find out. Is there an assumption about the nature of the forces that drive these fluxes here? Is there an analogous situation to say Fick's law or Fourier's law or something?
As far as I know, it doesn't enter into this. What de Groot does, I'm familiar with the derivation, he goes through a long list: mass, energy, conservation, these things. Then he gets to entropy and he says, aha, this is more difficult because it's not conserved. And so he rearranges some equations, and then he says, I'm going to identify this as being the entropy production term. So it's not really strictly rigorous, perhaps, but it is something that there's a lot of precedent for a lot of this. It doesn't mean it's correct. In fact, I have a bit of,
I thought that there was some sort of assumption about linearity.
About linearity. I think the way people analyze this is then they insert the linear relations here into either the gradients or the fluxes. Then that's how they solve it. And then you're getting into the Onsager regime. So that's how they actually, in practice, solve these things. I think that's flawed. So because of course it's not necessarily linear. Does that answer your question? Okay. All right, just a comment about analysis of a global steady state flow, and this was attempted by Dewar. So he considered what he called an open system, constrained by internal densities, so internal densities of different quantities and heat, or I should say internal energy, and boundary fluxes, and then he analysed the system in terms of what he called a path entropy, and where you've got a probability associated with a path. And I've read this work many times, and it always baffled me as to how he had done his analysis. And I suppose the advantage of what he did was he was trying to consider an entire control volume. And I can see although I have a formulation of an infinitesimal element, I can see the advantage of this, that if you can analyse a whole system, then you don't have to worry about some sort of integral over its constituent parts. Fine. And so that is a strong advantage. But since he published his work, actually a couple of people have written papers more or less pointing out some fairly important flaws in this analysis. So the analysis that he gave is actually invalid. It's not slightly invalid, it's entirely invalid. And so it's unfortunate that that is the case, but it does not actually give us a MaxEP principle. So that's the first point. And the second point is more of a philosophical one. It's when you're talking about probabilities and entropies, you've got to be very careful to say what it is that you're actually talking about. These are actually not probabilities of paths. When you actually look at his mathematics, these are more or less the same probabilities that I've used in my analysis. And I didn't realise this at the time, but these are just probabilities associated with fluxes. That's all they are. There's not a historical evolution of a system along a path through time. Time doesn't enter into any of this discussion. It's just an analysis of a steady state system, is what he was trying to do. What I can do though is, what I'm going to do here is reinterpret his work. We can apply exactly what I did to a global steady state flow system. Now we've got a boundary, so we've got to consider fluxes around the boundary, so it's a function of area. So we've got mean values of fluxes, instantaneous values. We've got probabilities associated with those instantaneous values. We can maximize this global flux entropy now and end up with something that looks the same, except we've just got the probabilities are functions of area, and we've got an integral over the boundary. But everything else maps the same. We have an entropy production, and we can recognize these terms in a similar way. And we can come up with this quantity here, where we've got an entropy inside the system and an entropy outside the system. And again, we get 2 out of 3 cases. That's going to lead us to a max EP principle. And 1 out of 3 cases, there will actually be a minimum EP principle. And I don't really see how you can do anything more with this, because it's identical to thermodynamics in terms of its mathematics. Okay, so that's more or less the analysis side. In terms of some unfinished business, you can prove that your sum of entropy production within the system is equal to its global entropy production. You would hope that's the case. It has to go somewhere. It's not conserved, but entropy is preserved. Once it's created, it is not destroyed. And if this really is a steady state system, then it must all be being dumped outside the system, and so therefore it must be passing through that external boundary. One slightly more challenging question is whether, when we maximize something at a global scale, whether we're going to attain the same optimum as if we take a sum of maxima at local scales. This is not a very trivial question, and this is something I'm trying to work on. And of course there's another question of what does a mean mean? And in actual fact, a steady state is inherently unsteady. It's steady in the mean, that's all. Now I'm going to talk about, okay, I probably don't really have time if I'm going to talk about some important things, but here you can just take more or less what Tribus did in his book. You can derive these laws of thermodynamics within the Jaynesian framework. You can map that over to laws of flow systems. So 4 laws. You get the same thing, first law, second law, third law. You've got a 0th law. Third law is interesting, is the zero state of the flux entropy is equilibrium. Okay, that's nice, right? So you end up, if you take an expansion like this, Taylor expansion, your linear regime just chops everything off and just leaves this first term. But you always have these reciprocal relations regardless. So the Onsager relations apply in general, not just in the linear regime. It's just they may be highly local. You might not actually be able to observe them very easily in a turbulent flow. And you can't read this, but you can actually, remember the matrices are first and second derivatives. These are the derivatives for a flow system. If I'd written this out more neatly, you'd see it in a matrix form. These are functions of your transport coefficients. So again, you have a nice relation and connection between, in this case, between flow and transient phenomena. So moving up the scales, if you like. You can examine these things from a point of view of Riemannian geometric framework. You can adopt this derivative here as a Riemannian metric, and you can measure lengths and distances, and using one of the inequalities, you can come up with this inequality. So it gives you a minimum, essentially a minimum cost for moving. This is a manifold of stationary positions, and it gives you a minimum cost to move from one position to another. And how does that work in practice? There's a field known as finite time thermodynamics, in which these people have recognized that there's a minimum entropy cost associated with moving from one equilibrium to another at finite rates. That's why they call it the finite time thermodynamics. Similarly, in a flow system, there's a minimum cost, and it turns out to be a minimum EP cost for moving a system from one steady state to another steady state at finite rates. Okay, now I'm going to talk about an example, and this example is actually entirely empirical, and I won't try and apologise for that. What I'm going to do is I'm going to consider flow along a pipe and express the friction loss in terms of this parameter, the head loss, or if you're a mechanical engineer, you'd multiply this by rho g and call it the pressure loss. But essentially, you have a head loss in a pipe, or a pressure loss term in a pipe. You have a Reynolds number. I put some absolute values here because I'm trying to account for direction of flow, so I'm just trying to be careful here. We have a laminar flow equation which relates this term, this friction factor here. This is essentially just a drag coefficient, or related to. So this is related to the Reynolds number in laminar flow. In turbulent flow, we don't actually have an equation. So the engineers have presented a bunch of equations here. And so this term here, the Colebrook equation, is something that we use in general. So these three equations here are entirely empirical. What I'm going to do is I'm just going to use these equations to interrogate the system and see what we find. So here's a diagram known as the Moody Diagram, which I teach to my students. So essentially what you have here is you have laminar flow over this Reynolds number regime here, and then there's a transition somewhere, so it'll follow laminar flow along here, and then there'll be some sort of transition in this zone, and then it'll follow one of these turbulent flow curves. If it's a smooth pipe, it'll follow this black curve, and if it's a rough pipe, then depending on the roughness parameter, then it'll follow one of those curves. Okay, done. Now you know my hydraulics lectures. What we can also do though, and something engineers don't traditionally do, is calculate the entropy production associated with flow. And so that comes out very easily. That's a head loss multiplied by the flow. And we can express that in a dimensionless form like this, and that's fine. And something that engineers do though, quite commonly, is they consider that pipes exhibit power law behaviour, and so there's a power law relation between the head loss and the flow rate. And you see here that the Onsaga regime would be a linear relationship here, so alpha would equal 1 here, and that would correspond to laminar flow. But we have the possibility of turbulent flow, and so just a very crude analysis using a power law, we can accommodate the spectrum of laminar through to fully turbulent flow. And when we rearrange our Moody diagram in terms of this dimensionless entropy production, so we've got the right scale now, you can see that the flow is laminar along here, and then there's a transition here, and lo and behold, it undergoes a transition to a state of increased entropy production. And this diagram, I will contend, looks very similar to those other diagrams that you saw for two other types of systems. And so this, in some way, it doesn't prove because I use the empirical equations, but it suggests that there is a connection here between all of these different types of phenomena. Okay, so now I'm going to talk about flow in parallel pipes now. So this is a little bit more complicated. And what I'm trying to do here, where I'm going, is that you can actually see some examples of some minimum EP and max EP principles that emerge in different types of flow systems. So parallel pipes, so the simplest example that you can possibly imagine. And what are the equations here? Well, you have conservation of fluid at the nodes, hopefully. And you also have that the head loss must be the same. The flows will readjust until the friction loss in one pipe is the same as the friction loss in the other. That's quite fundamental. Or you can think of this in terms of Kirchhoff's laws if you want to think that way. If they're parallel pipes, you'll write that this way. In general, they're not parallel pipes, and I'm going to use those empirical equations. This is deterministic. We have two equations, two unknowns, we solve, we're done, that's it. We get the solution. But some people have come along and said, aha, there's a min-EP principle here. And a la Prigogine, it's not Prigogine's principle. Prigogine's principle concerned different phenomena. So flow of heat in competition with flow of mass in competition with flow of something else. Here we just have competitions between flow of a fluid in multiple pipes. But he would write it this way, or some other people have written things this way, that we need to minimise this principle, minimise this entropy production in order to predict the steady state flow of the system. All right, and it turns out this is actually slightly correct. You can prove that it's correct if the pipes obey a power law, and both pipes obey the same power law, and there's no temperature dependence. So I'm going to call this a minimum or a pseudo-minimum power principle because there's no effective temperature. And so this you can use, and operationally it might be useful, but you can use to predict the steady state from the set of non-steady states in the flow system. But on top of that, we still have the Poltridge MaxEP principle, which we think is governing the transition between laminar and turbulent flow. And we can make a little plot of that. This is, what are my variables here? This is the total Reynolds number. So this is effectively the total flow through both pipes. This is effectively a flow through one of the pipes. So this is one of my parameters that I'm able to vary. And this is the entropy production. And you can see here that if you start off with a laminar flow, then it has high entropy production, then there's a transition, and then it will move to turbulent flow, which has high entropy production. So this is the steady state. But at each steady state, you can also draw a plot of the set of non-steady states, and you see that the steady state is minimum with respect to those non-steady states. And so you see both principles in play on the same graph, which is nice. But I would also contend, though, that this minimization principle here is quite trivial because you already knew where the steady state was. Remember, it was deterministic. So in some sense, this principle, minimization, doesn't help you, but this principle to decide whether it's laminar or turbulent flow, that's actually quite important. Okay, let's do things the other way around. So we're now going to be electrical engineers with slightly funny resistors. So we've got a head loss here, we've got flow between two pipes, but now we have a common head loss. But don't forget, we have the possibility of non-linear flows here. So unlike electrical circuits that only have Ohm's law, and so only have a linear relation, here we have the possibility of non-linear relation, or in other words, turbulent flow. So the head losses must be the same, and so that leads us to this relation. We no longer have conservation of flow at nodes. There's no, I mean, we have it, but we don't know what the flow is, so we can't apply that as a constraint. And so we end up with looking for something else. So we end up with the heat equals work principle is how people have cast this. And again, two equations, two unknowns, it's deterministic, we can solve it. But some people have come along and said, aha, there's a MaxEP principle operating here. And it turns out that you can try and apply this principle. In the same way that there was a pseudo principle earlier, there's a pseudo principle here. Again, it requires the same conditions, parallel pipes, both the same type, no dependence on T. So this is a pseudo maximum power principle or a pseudo MaxEP principle. But on the other hand, there's still a selection principle going on between laminar and turbulent flow. And when you use those empirical equations I showed you, there's an inversion. And I'll show you this. So here is the laminar flow. It has lower entropy production. Then there's a transition here, and then there's a turbulent flow, steady state, at lower entropy production. And in this particular situation, for various reasons, the last time these came out both sides, here we just have sort of comb-like structures. This steady state is a maximum with respect to non-steady state circumstances, but only on one side. But again, we see this competition playing out between a minimum and a maximum principle at the same time. But we, again, will contend that one of these principles is much more important than the other. So we plot a little diagram of this. Single pipes, if you've got a constant flow rate, we've got a MaxEP principle, which decides between laminar and turbulent flow. And similarly in parallel pipes. But we also have some pseudo principle governing the choice between the steady state and the non-steady state. But on the other hand, when we put a constraint now on constant head loss, or constant gradient, you can think of this. I didn't show you the example, but it plays out just in a single pipe. Or in parallel pipes, you have a mini-P principle here, but we also have the pseudo principle, and some papers by Zapanovic have worked on this. Unfortunately, this is not the MaxEP principle that we want to use, because it's not even correct, and it's trivial because we already knew the steady state anyway. And this thinking is actually coming out in some other papers, and last year I met Yoshida from Japan, who's also worked on this type of thing as well, and he, with some basically state function arguments, so nothing related to entropy or entropy production arguments. And again, he considers that there are certain types of systems that undergo this inversion. And so for planetary systems, it looks like there is a MaxEP principle, but in other kinds of systems, maybe there is a min-EP principle that we need to be thinking about, which governs the state of the system. So we have to be, this is just empirical, this is not proven, this needs to be explored in a lot more depth, but I just give pause to those who rush in and apply MaxEP to everything, that you really need to think about your system, and maybe MaxEP is not the principle that you want to be considering. All right, how long do I have to go? 2 minutes? 2 minutes? An example that you'll like, which I won't say too much about because it's not published yet, but I worked just recently with Bernd Nowak, who's a very well-known fluid mechanicist in France. And the way they do things here, and this is something I'm still trying to understand myself, is they analyze a fluid flow. Here's a velocity in a flow. They break it up, so they decompose the flow with this Galerkin expansion. And then they can use this, so they take the Navier-Stokes equation and map that into some equation of this type, which is essentially an orthogonal projection, and in terms of these, what they call amplitudes. And then the question is, well, okay, we can do this algebraically, but how do we estimate these amplitudes? And my collaboration was to work with him to implement a MaxEnt method for this, and we did. So we have an entropy here defined on these amplitudes. They're continuous, and so we have a continuous relative entropy here. And then we had to think a lot about the constraints, and so we applied some constraints from symmetry and from power balance type of considerations. And what was crucial here was we had to also choose a prior. Sorry, I've used the wrong symbol here. So Q of A. We chose a prior which reflected some understanding of the system, but only a fairly weak prior. And when we did that, we so applied this to the example that we applied it to was a cylinder wake. Here's this decomposition. So we can make a representation of the cylinder wake. We have a limit cycle. It's going around here like this, but it's also driven upwards, up some coordinate in this direction. So although you might think that the solution of the system should be here, should remain here, because of the cyclicity of basically the oscillating flow, you end up with the system is driven upwards and it's oscillating around some coordinate in this coordinate space. When we apply MaxEnt with this prior that I just indicated, you can come up with, so this is just with 2 modes, you can come up with a PDF prediction, which is very close to the direct Navier-Stokes solution. And obviously far, far less computationally intensive than that DNS. If you apply it to 6 modes, not quite able to represent it in this coordinate space, but if you look at the energy spectrum, so essentially what's going on here is this is the energy cascade. So energy's at this highest mode and then being transferred down through this cascade. And we're able to predict fairly closely the features of this energy cascade. So that's just a hint, and so look out for this. This is something that will be coming to the journals fairly soon. So in conclusion, I've analysed, well, first of all talked about the meaning of the entropy concept, then talked about Jane's mathematical structure, applied that to an equilibrium system, and also drew out this negative mass U function or potential function, which becomes an analog of a free energy on temperature, but it's something that is applicable to any system which is amenable to Jane's analysis. Talked briefly about the Maxell principle, then talked about how to apply MaxEnt to a steady state system, and you get this type of relation here where you've got an entropy, a different entropy, a flux entropy. So we've got changes of flux entropy inside and outside the system, and in balance, that sum must be maximized, and that means that this potential must be minimized. And then I talked about some other types of relations, local and global analysis and some other relations, and then a very empirical analysis of flow in single pipes and parallel pipes, just to explore some of these manifestations of these types of principles. Okay, thank you.
Questions? Yeah. Also, I want to just remind everybody to talk into the mic, please, so that we can record it, your questions. And also to the speakers, if they're not doing this, to please repeat the question, or if they jump up with a question during your talk, please repeat the question so that everybody can hear it and the answer too. Thank you.
In the last example, the one with the dynamical systems, your entropy is an entropy computed on the whole trajectory, the one you maximize?
It's a limit cycle. So it's, yes, it's over a trajectory, but you can think of it in the same way as a steady state. That it's not a transient flow that is, you know, changing it's changing in time, but it's changing in time according to a limit cycle. Yeah.
So it's a steady state that maximizes the entropy.
Yeah.
Okay.
Yeah. So it's actually quite analogous to the previous work, or somewhat analogous. And what's actually interesting here is you get the Lagrangian multipliers here come out with things with meaning, and it's actually very interesting. So it's not just something. It's something that you can quite recognise as a flow system.
Another question, if you don't mind. The analysis you did before with maximum entropy production for a thermodynamical system.
Yes.
Do you have a counterpart for an information system? An information system.
Information system.
Did you
no,
do something like that?
MaxEP for a flow system? Do you mean a steady state system?
Flow, but just as information, not
flow of information. Yeah, no, that's a very good question. I've been thinking about those. I showed you much earlier a generalized network. And in principle, a network can have flows of something, quanta. And so in principle, you can talk about bits of information. So you could consider an information system that way. I haven't tended to do that, but there's no reason not to do that. In fact, there's probably good reasons to do that. So in that sense, that would fit under this framework. But I don't see information as separate from any of this. Information is part of this. So although I take the Boltzmann principle, we're seeking the most probable state of the system, that can still mean it's an information flow. So I would certainly not rule that out. Does that answer your question?
Anyone else? Questions? Okay, I'll ask a couple actually.
I was waiting for you, Adam.
I want to give everybody a chance. So you mentioned César method of types, use the method of types. So I could be wrong, but so for instance, Cover and Thomas shows you get Shannon entropy from method of types derived from method of types, right? But the problem I have with that is that they're frequencies as opposed to Bayesian probabilities, correct?
Not
Can you
correct.
comment on that?
Not correct.
No, not correct.
Yeah,
okay.
not correct. Well, that's one interpretation.
Okay.
You said that in your talk as well. I'm puzzled by that.
Okay.
Because in the Boltzmann framework, you have this log of a probability, and this probability can be any probability that you want it to be, including a Bayesian probability. So it's not, all you're doing is maximizing a probability. And I've had long conversations with, there's a Bayesian group at Oxford, for example, and this is actually what they do. They maximize logs of Bayesian probabilities. So this is not unheard of in Bayesian inference. So I don't see why there's such sort of, I don't know, condemnation of the Boltzmann principle based on the fact that allegedly it's frequentist. So I don't see it as frequentist at all.
Well, and that would lead to the second comment I was going to make, which is that Jaynes had a nice paper that showed that numerically the Gibbs entropy connects numerically to the thermodynamic entropy as opposed to the Boltzmann entropy. So.
You said that in your talk, and I went back and I looked at that paper. That's 1965.
Yeah.
That is a different Boltzmann entropy. That's not the Boltzmann entropy that I'm talking about.
Oh, okay.
So we've got to be very clear. I mean, Boltzmann wrote, the criticism of Boltzmann by Maxwell was that Boltzmann would change notation and change symbols in the middle of papers and so on. So he probably caused a lot of confusion. I think the famous quote of Maxwell was, the more I read Boltzmann, the less I understand him. So, yeah, I mean, I take the point, and I've heard this critique before, that Jaynes disproved the Boltzmann entropy, but that is actually a different entropy. That's a one-particle entropy rather than a multi-particle. It's a specific example which Boltzmann used in his H theorem. It's not this Boltzmann entropy, which is just a log of a weight or log of a probability. So, but yeah, I'm happy to take up this subject more. I mean, there is something more deep in there that which needs to come up to the surface. But you can actually show, I spent a number of years in combinatorics, combinatorial basis of entropy before I came into this area. And there are systems, and you might say they're contrived systems, okay, but you can design systems where if you maximize the Kullback-Leibler, or the relative entropy, you end up with a prediction which vanishes. It's not representative of the system. So what are you trying to do? Are you trying to describe the system, or are you trying to insist that there's only one entropy function? I don't know. I think if we accept that all of this is just probabilistic analysis and we're just maximizing probability, maybe we don't even need the concept of entropy. Maybe that's unhelpful. So I don't know. But
okay, fair enough. Thank you. Any other questions? All right, let's thank the speaker, please.
Thank you all.